Hello, everyone. What I want to do now is finish up the basics of compound interest part 3. And in the next video, what we'll do is discuss the force of interest. Essentially, it's a continuously varying interest rate, how to handle situations like that. And then we'll dive into annuities. Right? So remember last time we talked about the effective annual discount rate, and we had a bunch of formulas connecting the effective annual discount rate, the effective annual interest rate, and the present value factor. Right, so I want to do two very easy examples just using these formulas. All right, so first assume that $2,000 was worth $1,568 5 years ago. Assuming a constant effective annual interest rate for these 5 years, find both this and the effective annual discount rate.
Okay, so I want to actually do this example two different ways. First, using the discount rate, and then secondly, using the interest rate, or rather the effective annual discount rate, and using, secondly, the effective annual interest rate. So first, using the effective annual discount rate, and I should say that the fact that I'm even using the term effective discount rate should hint that there's going to be nominal discount rates, coming up, and that's exactly what we'll do next. Okay, so we are given that 1568 is the present value of $2,000 due in 5 years. So our formula for present value is just that D is the effective annual discount rate, then 1568 is 2,000, 1 minus D to the 5th. So you just solve for D using simple algebra, and you get that D is going to be 1 minus 1568 over 2,000 to the 1/5, which is 0.0475. And plugging this into our formula for the effective annual interest rate, so it's just D over 1 minus D. We get that the interest rate is 0.075 over 1 minus 0.0475, which is 0.04987. All right, so just to get some extra practice with our basic formulas, as I said, I want to also do this using the effective annual interest rate. First solving for that, and then using that to solve for the effective annual discount rate. So using effective annual interest rate, well, just use our present value formula. The present value of 2,000, which we know is 1568, is given by 2,000 1 over 1 plus I to the 5th. So you just solve for I. You get that I is going to be 1568 over 2000 to the minus 1 over 5 minus 1. And this is going to be 0.04987, which is exactly what we got before. Better be. And dump this into our formula. We get d is I over I plus 1 is 0.0475. Okay, which again is exactly what we got before. So doing either method works. And I just want to make one quick comment, just to remind you, both formulas that we used, in general, present value of k due in n years is going to be using the effective annual interest rate I. It's k 1 over 1 plus I to the n. So maybe I shouldn't put a colon here. That. So this present value is equal to this here, which is also 1 minus d to the n. And for this reason, some people call this term here, well, they're going to be the same, what's in the red, but because they're the same, some people call what's in the red the present value factor. Some people call it the discount factor. Some people, probably like myself, probably use both in the same example sometimes. But, you know, they're equal. And, you know, because both basically serve the same purpose, just this, you know, this, they're the same. It's just this is in terms of interest, this in terms of discount. But you take either of them, raise it to the n, multiply by k, you get the present value. So sometimes it's called the discount factor, sometimes it's called the present value factor. But anyway, so just want to make sure that's absolutely clear. So another very simple example is the following. Yeah, so if we have the effective annual discount rate is 0.07, then find the present value of 5,000 due in 3 1/4 years. So there's not all that much to this problem. You just plug and chug here. So the formula, switch to black pen. So the present value of 5,000 due in 3 1/4 years. Just use the formula I had before. Your discount rate, effective annual discount rate is 0.07, so it's 1 minus d to the, well, 3 1/4 years is 3.25. So you just plug into your calculator. This is 3,949 and 48 cents.
The concept of a nominal discount rate is really kind of the same as the concept of a nominal interest rate. Okay? So what does it mean to have a nominal discount rate of d superscript m compounded m times a year? Well, you basically just, you know, the meaning is just simply d superscript m over m is the discount rate, the actual discount rate for the compounding period of 1 over m years. which just means that money loses exactly this percentage of its value per 1 over m years moved back. Okay, that is the definition of this d superscript m. This is the, by d superscript m, it means exactly this, that money loses d superscript m over m times 100% of its value per 1 over m years moved back. Okay, so let's figure out a way then to get a formula relating d superscript m and the equivalent effective annual discount rate. And it's not particularly hard if what I did for nominal interest made sense. Particularly, we know that if we have a discount rate as a decimal, then we just take 1 minus that discount rate to get the present value factor. So divide by 100 to go from percentage to decimal. The discount rate per 1 over m years for that time period, rather, is d superscript m over m. So 1 minus that is the present value factor for a time period of 1 over m years. And we discussed that in detail in the previous video, the idea of if you have a discount rate, 1 minus the discount rate gives you the present value factor. All right. Right. So that means we can get the 1-year present value factor by compounding this m times, because, well, 1 minus d superscript m over m is the present value factor for a time period of 1 over m years. So if we keep discounting that same present value factor, if we do that m times, we're discounting m times the time period of 1 over m, which gives us the same, which has the same effect as doing a 1-year discounting. Okay, and so that means the 1-year present value factor is just 1 minus d superscript m over m raised to the m. Okay. So again, this is very analogous to what we did for the 1-year growth factor for a given nominal interest. And there it was the same thing. You compound the 1 over m year time, the 1 over m year growth factor m times. Here we compound the 1 over m present value factor m times to get the 1-year present value factor. Okay. Well, again, we know that if we're given a 1-year present value factor, then the corresponding 1-year discount rate is 1 minus nu, and we have nu in terms of this nominal discount rate. So, right, so we get that if d is the 1-year discount rate, the equivalent effective 1-year discount rate, or the equivalent effective annual discount rate, then d is given by 1 minus, parentheses, 1 minus d superscript m over m. So to summarize, and I have to admit, I use d here and d here, which maybe isn't the best, but as I explained here, d is the equivalent effective annual discount rate. So just to summarize, given a nominal discount rate, d superscript m, the meaning of that is the effective discount rate over a time period of 1 over m years is d superscript m over m. And the equivalent effective annual discount rate is 1 minus parentheses 1 minus d superscript m over m raised to the m. Okay. Now let's suppose instead we were given an effective annual discount rate. Okay. You can very easily solve for d superscript m in this formula here. You just subtract 1 minus everything, raise both sides to 1 over m, et cetera, et cetera. And you get the formula for d superscript m given an m and given an effective annual discount rate. It's just m times parentheses 1 minus parentheses 1 minus d to 1 over m. Very easy to get that. Okay. And just like with interest, whenever I say effective, I mean the actual discount rate. Whenever I say nominal, I mean exactly what is here. By definition, nominal discount rate d superscript m means, again, the effective discount rate for a period of 1 over m years is d superscript m over m. Okay? I should mention that the calculator will do all these calculations from nominal to effective interest, and I'll explain in future videos. Might even be up actually, how to do that. I don't remember if it's up or not, but it's still, in my opinion, I think most people's opinion, it's very important to really have a good working understanding of, you know, how to go back from nominal to effective interest and discount, and particularly to just understand what nominal, discount, and interest means. So for now, we're not using the calculator to go back and forth. Okay. Yeah, so let's say now, just like with interest, we want to let m go to infinity. So the nominal discount rate, delta, or d superscript infinity, which is kind of weird to write, so we use delta, compounded continuously, is, well, just take the formula for d superscript m, let m go to infinity, and this is a infinity times 0 form. So I recommend everyone try this yourself, to use L'Hopital's rule to figure out what this limit is, particularly if you're a math major, actuary major. And if you do that, you'll get it's minus ln of 1 minus d. But 1 minus d is 1 over 1 plus I. You can check that, just a little bit of algebra, because d is I over 1 plus I. And we know, or should know, ln of 1 over I plus 1 is minus ln of I plus 1. So we get some kind of cute little interesting formula here that discount compounded continuously is the same as interest compounded continuously. It's both the same formula. Delta is ln of I plus 1. This is not a terribly deep fact, but it's a curious little fact here. Yeah, and the idea is same thing with interest. Let's say m is very large, so that could, you know, for example, would mean you're compounding interest every hour, you're compounding interest every second. You know, every hour would correspond to 365 times 24, which is 8,000 something. Times that by 60 to get interest compounded every minute, et cetera, et cetera. And you know, this kind of quantity here is a bit messy. It's a bit annoying, unpleasant, whatever, for m large versus ln of I plus 1, which is a lot, or minus ln of 1 minus d, same thing. It's a lot cleaner, a lot easier to work with. So this delta is a good approximation for nominal interest compounded over a very, very small time period. And just like usual, we can solve for d, right? So if we're given delta is minus ln of 1 minus d, you solve for d, minus both sides, then raise it to the e, then minus both sides again, subtract 1, you will get that d is 1 minus e, the minus delta. If we're given a nominal, sorry, it should be discount rate. It is the same thing. As I said, delta is a nominal discount rate. It's the same thing as a nominal interest rate. So if we're given a nominal discount rate / interest rate compounded continuously, then we can solve for d, as I just mentioned. D is 1 minus e to the minus delta. All right, so let me do a very easy example. Yeah, so let's say I have a liability due 10 years from now, and it's valued at $15,000 today. Find what X is in all these situations. Discount is compounded monthly at 6%. Discount is compounded continuously at 6%. Nominal interest is compounded monthly at 6%. Interest is compounded continuously at 6%. Right, so it's fairly straightforward, plug and chug. But this does illustrate an important point, as we'll see, that no matter how interest discount is compounded, we get roughly the same answer. It's not exactly the same answer, but we're roughly going to get the same answer. I mean, there's enough differences in the answers for it to matter, absolutely. But for the purposes of taking an exam or quiz, you know, if you do this and you get different answers, like that differ in the thousands, you obviously did something wrong.
Okay, so let's do 1 through 4, and in each of 1 through 4, let's solve for the liability X. So in 1, we're given that discount is compounded monthly, so M is 12. We're given the nominal monthly discount rate is 0.06. So let's get the equivalent effective annual discount rate, D, and just plugging into the formula, it's 1 minus D12 over 12 raised to the 12. Well, we know D12 is 0.06, so get rid of this. Throw in 0.06, and you get 0.05838. Okay, so we know by the formula for present value, well, 15,000 is present value of this liability due in 10 years. Right, the formula is the present value of anything, X here, is X times 1 minus your effective annual discount rate raised to, here it's in 10 years. So my liability is 15,000 over 1 minus 0.05838 to the 10, which if you put this in your calculator will be 373 and 76 cents. Right, so let's do 2. Here we're given that discount rather is compounded continuously. So our formula, our discount compounded continuously is given by 0.06. So our formula for the equivalent effective annual discount rate, D, is just 1 minus e to the minus delta. Well, delta is just 0.06. So this is going to be 0.05824. And again, just like before, solving for x, in this case, the value of the liability, x is going to be 15,000, basically the same setup, 15,000 over 1 minus d, 0.05824 to the 10th, which is 27,331 and 78 cents. And both answers here, you'll notice, as it should be, both D and X are very similar in these two here, as they should be. So remember I said for nominal interest, it doesn't really matter how often nominal interest is compounded. It doesn't even matter all that much nominal interest versus effective annual interest. You should get roughly the same answer. And same thing with discount. And 1 and 2 shows that. So let's just get 3 and 4 quickly. So 3 is basically a review. So we're given that I12 is 0.06, M is 12, interest is compounded monthly. So the equivalent effective annual interest rate, 1 plus I12 over 12 to the 12th minus 1, and I12 is 0.06. So this is going to be 0.06168. So certainly not that you would think it should be that close, but discount and interest don't really have to be that close to each other. But let's get X here, and that should probably be, well, let's just get X here. So in this case, 15,000 is the present value. And the formula is just X times 1 plus your interest rate, your equivalent effective annual interest rate, raised to the 10th. So X here is just 15,000. Well, this is just 1.06168 to the 10th. And as a sanity check, this makes perfect sense. All we're saying here is the value of this liability is 15,000 accruing 10 years of interest at an effective interest rate of 6.168%. And so this is going to be 27,291 and 51 cents. Okay, and for 4, last but not least, again, kind of review, we're given that delta, we're given that interest is compounded continuously, so M is infinity. Delta, make it look more like a delta. Looks a little better. Yes, anyway, delta is going to be 0.06, and the equivalent effective annual interest rate is e to the delta minus 1. So it's e to the delta. Well, yeah, delta is 0.06. Make that look better. That looks better. And this is going to be 0.062, which this is very close to 0.06168, as it should be, because as I said, it doesn't matter all that much if you how often you compound nominal interest. You should roughly get the same answer, particularly for the equivalent effective annual interest rate. And so, right, so again, just like before, X is going to be, just like the logic of 3, 15,000, 1.062 to the 10th. Let's see something here. Sorry, I made a mistake here. You plug this into the calculator, this is going to be, it's actually even closer to the equivalent effective annual interest rate in 3. It's 6184. So yeah, this one's 6168, 6184. So even closer. Okay, sorry about that. So it's 6184. And you put this into the calculator, you get 27,332 and 67 cents, which is awfully close to X in the previous example. 27,291.51 cents. Only off by a few dollars. Okay, let's do another quick, easy problem here. So for one, let's get the equivalent effective annual interest rate, and let's check our answer. And in particular, for one, let's check that the present value of our liability that we found is actually $15,000. Okay, right. And I do want to check that the equivalent effective annual interest rate we get in 1 is fairly close to what we get in 3 and 4. Okay, so, right, so here, so remember in 1, we have discount is 0.05838. Okay, so our formula for the equivalent effective annual interest rate is just D over, remember, 1 minus D, and we just had D is 0.05838. And this gives me 0.062, which is fairly close to the interest rates we get in 3 and 4. Okay, and we got, remember, in 1, the present value, or the liability rather, is worth $27,373 and 76 cents. Yeah, so let's check what we get. So the present value of $27,373 and 76 cents due 10 years is going to be 27,373.76 times 1 over 1 plus 0.062, 10th, and we get 15. Right, we get 14,999 and 93 cents, just due to the rounding and getting I here. So we're only off by 7 cents from 15,000, just due to the rounding for computing I. So basically doing it this way checks out. We get, what we expected, roughly 15,000 is what the present value of the liability is. And also we also rounded for this quantity here. So that's another source of error why we don't get exactly 15,000 when we check this. Okay, and right, so a few more easy problems. Right, so if effective annual discount is 7%, then find the equivalent nominal monthly and continuous discount rates. Okay, so this is fairly plug and chug. So we're given that, let me go back to black here. So D, our effective annual discount rate is 0.07. Now let's just plug in what we want, monthly nominal discount. So that corresponds to M equals 12. So just plug into our formula, D12 is going to be 12 times 1 minus D. So this is D here. Raise that to the 1 over 12. Sorry, raise this to the 1 over 12. And we're going to get 0.07235. On the other hand, our formula for delta, nominal discount compounded continuously, is minus ln of 1 minus D. So that's going to be minus ln of 0.93. 1 minus 0.07, and that's 0.07257. So roughly the same answer, again, as it should be. Because it shouldn't matter all that much if we're, how often we're compounding nominal interest. If we have the same effective annual discount rate, then we roughly should get the same answer no matter how often we compound discount.
Okay, so I want to end off with simple discount and interest and how it relates to present value. So the concept of present value with simple interest is, no pun intended, very simple. It really is not complicated. So let's say we have simple interest at 7%. Let's say I need $100 in 30 days. What is my initial investment, A0, if this account accrues simple interest at 7%? We'll just plug into the formula for accumulated value. It's 100 equals A0, 1 plus my simple interest rate of 0.07. We're using 365 days in the year. So the fraction here is 30 over 365. And divide by this whole thing here, and we get $99.43. That's how much I need to invest now in this account at simple interest of 7% to get $100 in 30 days. If that makes sense, you understand present value when it comes to simple interest. Okay? So to basically generalize this calculation, the formula is the present value of K due in T years is just K is 1 plus I T. K over 1 plus I T. That's exactly what we did here. K is 100, T is 30 over 365, and I is 0.07. So I don't think there's really a good conceptual description of simple discount. It's just, kind of analogous to discount. When interest is compounded, we kind of want a present value formula described by k times 1 minus dt instead of k over 1 plus it. I mean, why we really want that, I don't know if I can even give a good answer for that, but people do want present value described in that way. So, so basically, D is just a decimal, a rate that describes present value according to this formula. And you can really, maybe the proper way of thinking about D is that this is really the definition of D. It's that if we're by definition, if we're given a rate D, a simple annual discount rate of D, then the meaning of that is present value is given by this formula. Okay, so one example of simple interest and discount is treasury bills. So later on, we'll talk about bonds in more detail. And well, actually, if you want to learn about bonds, all the bond videos are already out from previous semester. So I describe bonds in a lot of detail. So what is a T-bill? It's different from a typical bond. The idea is extremely simple. Again, no pun intended, because we will use simple interest to describe treasury bills. But so the idea is you pay the present value of K due in time T to redeem this amount in time T. So it's a very straightforward, simple investment that I would say is largely made when you have a lot of money and you want something extremely safe. And this is offered by the U.S. Treasury. All right, and here simple interest is used. All right, so I took this chart. This chart was taken according to the book. It was taken from treasurydirect.gov from March 2015, describing the interest and discount rates for these treasury bills. Okay, so what I want to finally do is verify these investment and discount rates. So investment rates is just it's really interest rate. So let's derive these rates and check that they're accurate. And this is for this row right here, a 91-day row. All right, so it's a bit bizarre, but for when you are working with a discount rate for T-bills, you're going to use 360 days in a year, whereas when you're using, so this got cut off a bit, but yeah, sorry about that. 1 second, sorry about this. There we go. Yeah, whereas if you're using investment rate, you're going to use 365 days in the year. It's a little bit bizarre, but that's just the way treasury bills work. It's a strange peculiarity of treasury bills.
Okay, so let's verify what's in the table. So, right, let's just use our formula. So we're given that the present value, or really the actual price of this T-bill, 91-day T-bill, is 99,989,889. And the value is given by the present value of $100 using simple interest. We just dump into our formula. So remember the convention, 365 days in a year. For simple interest, okay, so simple algebra is going to give me that if I solve for I get 0.000406, and this is going to be 0.0406%, which is pretty close to what's in the table. Let's go to the table. Right, so round my answer 0.0406 up to the nearest hundredth, thousandth decimal. We get exactly what's in this table here, 0.041%. Right, so let's check for discount. Okay, so for simple, so here, simple interest. Let's check table for simple discount. And it's really, again, going to be just plug and chug. So 99989. Again, this is the value of this T-bill, the price of this $100 T-bill, which is just the present value of $100. And just the formula is 1 minus D91. And remember the odd convention. It's 360 days in the year when we're doing discount. And you solve for D, we get 0.003999, which is a discount rate of 0.3999%. And that's very close, rounding to the table, which is 0.04%. Okay. So yeah, they check out the 0.041 and the 0.04% values in this table.